conditions for C star calculation, those things you should practice in tutorial with the data. Okay. So today we'll start fatigue, and once fatigue is over, then we'll talk about creep fatigue. And when creep fatigue is over, creep fatigue will not be too big. And then if the time is there, we'll talk about environmental assisted cracking. Okay. So what is fatigue? What is the meaning of it? Daljit, huh? What is the meaning of fatigue?
So due to cyclic loading.
No. Out of mechanics, what is the meaning of fatigue? In normal, usual days when we talk about
Coward.
what?
Coward वगैरह हो जाती है.
Coward.
मतलब
Coward बोल रहा हो?
Coward वगैरह.
थकावट बोल
Tiredness.
रहा हूँ. थकावट.
Tiredness.
हाँ. थकावट, tiredness.
So,
And what do you think fatigue is? इसका usual normal meaning क्या है?
वही है, ज़्यादा वर्क के बाद
थकावट ही मीनिंग है. तो हम थक जाते हैं तो मटेरियल भी थक जाता है. तो मटेरियल in many ways is acting as a human being, right? Strain hardening हो रही है, softening हो रही है. Every material has its own personality, right? And then if you look at atomic scale, every atom has its own type. So we will start with very basic. What we do, not that basic also. So fatigue is basically if you take something and you just do this. You can do it with your pen if you like, and it will break. Your pen will break in one cycle, half cycle. Okay, so that doesn't require fatigue. एक ही बार करोगे ऐसे टूट जाएगा. Okay. But when you have to break, like for example, aluminum wire, then doing this will not break it, pulling it will not break it, right? But if you do fatigue, then it will break it. If you do cyclic loading. Why?
So cyclically compression and tensile loads are
both in each cycle. When you are doing this,
yes.
In one cycle also you are giving tension on the outer fiber, compression on the inner fiber.
Compressions.
Yes. So then why it is breaking easily in fatigue and not breaking easily in monotonic loading? And the other question is, do you think cyclic loading can break materials even below yield strength? So below yield strength, we think elastic deformation is happening. So do you think below yield strength, material will break if you apply fatigue loading, cyclic loading? Should it break?
So Wishingers effect something like.
पहले तो ये बताओ टूटेगा कि नहीं टूटेगा, उसके बाद बाउशिंगर इफेक्ट की बात करेंगे. Yield strength के नीचे, when you are loading it, will it break or not?
It breaks.
Why? So below this point, you have elastic loading. So whatever load you apply, that should be recovered, isn't it?
Minimal amount of plasticity is also there.
So why do you think even below yield strength, if I apply cyclic loading, it will break, and if I apply monotonic loading, it will not break? That is pretty obvious from stress strain diagram. So fine, there is some plasticity below yield strength, but monotonic loading is not breaking it. Cyclic loading is breaking it. Why? So what Saurav is saying, there is some amount of plasticity even before yield point. Okay, why? There is some amount of plasticity even before yield point.
dislocations were also
Some dislocations are
piling about the
before
obstacles.
piling they will move.
Yes.
So they are moving even below yield strength. Why? How? So why do we call it elastic below yield strength?
So because no significant plasticity.
Yes. So
Yes.
if it is not significant, what should we call it?
Elastic.
If it is not significant plasticity, should we call it insignificant plasticity? Localized plasticity. So localized plasticity is happening. What do we mean by that? Why it is local? Okay, fine. So some plasticity is happening which is not measurable. You can't measure it. Okay? So why this plastic deformation, which is very small, will not break the material under monotonic loading, but it will break it in cyclic loading. That insignificant amount of plasticity is able to break material in cyclic loading, but not in monotonic loading. Why? Why? So in order to change, there are different personality types. Every people has some kind of personality, type A, type B, blah blah. Okay? And the personality usually does not change. Usually it wouldn't change. If you want to change a personality type, what should you do? If I have to change your personality type, what should I do? What are the events which can change the personality type of a person, not a metal? Sudden change in the environment. It is not cold or hot environment I'm talking about. For example, at the age of 19 or 20, instead of being normal Daljit, if you become Daljit Dosanjh, so you become very famous and you get a lot of glamour. That will change your personality. It has to be sudden and it has to be too high. Okay? So if you win a lottery of $1 million and you suddenly become rich, so that will change your personality type. Sometimes very drastic trauma can change your personality type. Right? And then we have some kind of mental sickness also. Not everyone is clinically sick, but some amount of damage is there in everyone. So if the trauma is too high in one event, that can cause, so for example, those people in army who go and have seen the fights, they have been found to be sick with PTSD. Okay, so post-traumatic stress disorder, because they have seen the worst people can do, and that stays with them, that creates nightmares and other things. But that kind of stress disorder, that's a clinical disorder. Okay, and we are not stressed by those because we don't see it. But so that is analogous to a monotonic loading. Okay, in order to break something in one go, you have to give it a very high value of stress or strain with impact at high temperature. All those things are happening. So basic mechanism is movement of dislocations, right? Whether it is cyclic loading or whether it is monotonic loading. Okay. So a person, a healthy person, if you want to break things, or then you have to give a very high traumatic environment to obtain what you want to do. But during the life period, you have a lot of stresses which are of not that high value, but they're there and they come and go and they come and go. and that also can cause some kind of damage in the people. Okay? So what do we think? We think that if the stresses in normal life, everyone has stresses in normal life, and if those stresses are very normal, for example, noise by the neighbors, or I don't know, something happening at the work, those who are working in sales has some target to achieve, those kind of stresses are there. So you think that some people can survive it, some people cannot survive it. Those who can survive it, for them you can say that you can apply infinite amount of this kind of stress, work stress, and they will live until retirement. You cannot create damage in them. They are trained specifically for that. Not everyone can go in marine, you need to get training. Once you get trained, then you can do those things, even though those are stresses, right? So analogous theory is there in fatigue. What happens when we do monotonic loading? We have grains, and in these grains, at any value of stress, you will have critical value of resolved shear stress. And based on the orientation, every grain will achieve this CRSS at different values of stress. Not all the grains will be perfectly aligned in one direction, so you will not have CRSS same or the same value of applied stress in the material. So every grain has different value of applied stress. Every grain has, for the same material, will have same value of CRSS. Okay, critical result CRSS value will be same, but the applied stress is in different direction for each grain. Okay, so that will cause a different value of applied stress so that it crosses the CRSS for each grain. Right? Is it okay? So each grain will have a different value of stress at which dislocations will start moving. So in some grains, these dislocations can start moving earlier, and in some grains, it will act at a later stage. So at those grains, in those grains where these things are happening earlier, they will start deforming earlier, and then if you keep on increasing the amount of force or stress which you are applying, then even the remaining grains will start deforming, so dislocations will start moving in those, and there will be a stage when all the grains will be deforming, or 90% of the grains will be deforming. So there we will have significant amount of plasticity to be observed, and we will have yielding phenomena. Okay, but before that we'll have some grains where we have some deformation, and that will not yield to significant plasticity, but it will be localized, right? So what will happen? Dislocations will move, and screw dislocations will move easier than edge dislocation. They will interact, and they will find a particle, a precipitate, or a boundary where they will get piled up. Okay, and then this piling up can be broken by cross slip. So if there are dislocations, and these dislocations, they see a particle, or they see a barrier beyond which they cannot go, but this barrier exists on this plane and a plane higher than that, but not a plane above that. So if the conditions are good, this dislocation will cross slip to this plane, and then it can cross slip to that plane, and then it can pass through, so it can overcome that barrier. It will not cross slip if there is no barrier, right? Because there is no reason to do it. Okay? And cross slip is good if you have high stacking fault energy. Okay? Because cross slipping usually happens when a perfect dislocation dissociates into partials. While cross slipping, screw dislocation it starts with the screw dislocation, the cross slipping. So if you have a dislocation loop kind of thing, okay? So, and this dislocation loop is moving in this direction. So this part is edge dislocation, because this is the dislocation line and this is the Berger vector. And this part is the screw dislocation, because Berger vector and dislocation line both are in the same direction. So screw dislocation does not require a plane to move. Edge dislocation requires a plane to move because you have a line and you have a Berger vector and both of them are at 90 degree. So you need a plane. For screw dislocation you don't need a plane. It can move. Okay? And screw dislocation, so it can change the plane from one plane, it can go to the other plane very easily. So for this loop, the screw dislocation part, the screw part of this dislocation loop will go to the next plane first, and then each segment of this loop will turn at one point to screw dislocation, and that will cross slip and the whole dislocation will move. Before that, this dislocation might be, and usually are, dissociated into partials. So there is a stacking fault associated with it, and that requires a stacking fault energy. In order to cross slip these, so if you have a dislocation which is dissociated into partials of type A by 6, 1 to 1, right? And this will be the counter part of it, some variation of 1 to 1. So when this has to change the plane,